Bismillahirrahmanirrahim. Hello again. This video will be continuation from where we left previously, and in this presentation I will be mostly talking about the system modeling itself. So let me start off by telling you about the mechanical design of the robot itself. So the robot that we designed was done so by using microcontroller Arduino Uno, and for motors we went with the Pololo 370X70L with a gear ratio of 71 and these motors were controlled by motor driver L298. And to control the angular displacement, calculate the speed and the angular displacement, we use the 3-axis control gyroscope MPU 605. And the robot design that we designed looks something like, as you can see in figure 4 from the front, and in figure 5 from the side. So the robot was capable of taking in some sort of disturbance and being unbalanced, and so we added these supporting sticks as well to allow the maximum angular displacement that our controller could able to handle. So moving on to the physical and electrical parameters. Once we had designed the robot, the next step was to calculate the parameters, electrical and physical, of the robot, which will then aid us further to substitute the parameters or the variables in the transfer option expression that we obtained earlier. In order to obtain these parameters, we simply used data sheets in certain cases and simple physical apparatus to calculate physical dimensions in the other. So this table 1 you see right here gives all the parameters for the mechanical robot that we calculated individually with their units. So once we had these parameters, the next step was to find the control force limit, which was basically the force that had to be produced by the motors on the robot, such that the robot will produce whenever there is some sort of disturbance impulse. In order to do that, we simply use the expression for the motors itself. Since we had two of these motors, so the the force that will be produced by the motors will be given by the by the equation 14, and similarly equation 15 gives the torque induced by the individual motor. We substitute couple of other expressions itself to finally get the equation 19. The equation 19 gives us the final force input that we will be that our motors will be able to produce, and then we can simply substitute the parameters that we calculated from the table 1 into the equation 19. Once we did so, we find that whenever there will be an impulse input, both the motors combined will produce a U input of 258 Newton, which will be the force exerted by the motor on the robot to balance it once there is an impulse disturbance. Right. Now let us talk about the simulations that we performed for the obtained transfer functions. We use MATLAB to simulate the response and the behavior of the system, and we can clearly see that for the card position on impulse disturbance, and also the pendulum angle on impulse disturbance as given by figure 6 and figure 7 is clearly unstable, and the system eventually blows out. Similarly, for step disturbance, we can see in figure 8 and figure 9 that the system also blows out, and thus we can conclude that the system is unstable. We also did root locus analysis, which I will discuss in about a while. But before that, let me just talk about a bit about the design requirement. So the robot that we designed, the controller that we designed for the robot was such that it will be the settling time for that robot had to be less than 5 seconds, and the rise time to be about less than or equals to 0.5 seconds, whereas the pendulum angle theta should move no more than 20 degrees on either side, and also the steady state error should be less than 2% or within 2%, and overshoot should be less than 20%. Once we had that, I will jump onto the controller design, but first let me just touch upon the root locus. So we use MATLAB again to do the root locus analysis of the system, and we can clearly see in figure 10 and figure 11 that the root locus for the horizontal displacement and the root locus for the angular displacement function both have roots on the right half plane, which clearly states that the system is unstable, and thus we need to design a controller that should be capable of shifting the root locus towards the left half plane and thus be able to stabilize that system, right? So so the controller that we designed was basically was done so in two parts. The first one, they are dealt with a digital controller that was implemented completely through Arduino coding IDE, and the second one was basically done on the MATLAB using the CISO tool. We will talk individually about both of them, but first let me just jump onto the physical control, the controller that we designed on the MATLAB. Right. So here on the screen you can see that we use the CISO tool to design a controller for our system, and by PID tuning that we did, we found out that if we place our 0 at 1/68 or minus 1/68, then we will be able to shift the whole of our root locus on the left half plane, and thus the system will be stable. As we can see that the two-step response, that is the amplitude, the angular displacement eventually turns back to 0. We did this analysis only for the angular displacement because at the time being we were only concerned with controlling the angular displacement, or rather than focusing on the horizontal displacement. In the future, if I do make some changes for the horizontal displacement as well, or study its analysis and behavior using the CISO tool, I will upload a update video. But for now, we only did analysis for the angular displacement. So this was it for the controller that we designed using the MATLAB CISO tool. The next step in this project was to implement the whole digital controller using the Arduino, for which we implemented it both through the built-in library that is provided by the Arduino, the PID library, and we also implemented it right from the scratch on our own. So the PID algorithm that was implemented by Arduino was done so by my partner Khwaja Ghulam Alamdar. I will ask him if he can make an update video on the PID algorithm for our system design. But for now, I think we are pretty much done with the documentation of this project. So I have also uploaded a video on YouTube which shows the response of the digital controller that we designed, and how it helps our system to stabilize. So we were able to obtain quite good stability with our robot, but there was still a lot more room to be improved, to be tuned, to be refined. So in future, if in near future we done some other work other than this on the project, then I will surely update you guys with an additional video. But for now, this is it. So yeah, Allah Hafiz for now, and do take care.